Sidman from NTNU, who is going to talk about the infinite décalage construction.
Thank you for inviting me to give this talk. I'm very excited to be here. Obviously, the community and also Edinburgh is such a beautiful city. So, yes, as mentioned, I'm going to talk about the infinite décalage construction. So this is a joint work together with Achim Krause and Thomas Nikolaus, which has been going on a while, but now we've been working on it a bit more intently. So all of this is kind of related to this project that we have on spectral sequences and maybe more specifically than trying to understand really what convergence of a spectral sequence actually is structurally, because I think a lot of people have maybe some misconceptions or some misunderstandings about this, and there's some things about it that are perhaps not maybe we think as being like structurally satisfying. So I will start by saying some words about spectral sequences just in general, so that we're all on the same page, unintended, I guess. Sequences. Okay, so I mean, I'm sure most of you have seen spectral sequences before. You know kind of what data they are. I mean, you have the pages of the spectral sequence, you have the differentials on the pages, and then you have isomorphism. So if I take homology with respect to the differential on one page, I should get the next page, right? So I'm not going to write that down. I'm going to assume that you kind of know that, but of course, like if there's any questions, you should feel free to tell them. So why do we actually care about spectral sequences? I don't think that spectral sequences are really interesting mathematical in their own right. I think we really care about them because like we care about filtrations, right? They're a very nice way of of like packaging the information available in a filtration of the mathematical object in a very nice way so that we can kind of process that information in using like homological algorithms. We care about spectral sequence, or at least that's my philosophy, right? So we care about spectral sequences because we care about filtration. Okay, so during this talk, I'm going to think about, well, we're all homotopy theorists here, so I'm sure we're all like comfortable maybe with the infinity category of spectra. I'm going to think of like having filtrations of spectra. You can also think of having filtrations in some other stable infinity category that I'll define, but I'm going to stick with spectra in this talk. So you have some sort of filtration of spectra for me, or filtration, like I said, in some other stable infinity category. And to this filtration, I associate some spectral sequence. And if I'm working with filtration of spectra, it's going to be a spectral sequence of 1 billion groups. In general, if I have filtrations in some other stable infinity category equipped with a T structure, I'm going to get a spectral sequence of objects, the objects being in the heart of that T structure, right? So for example, if I have the derived category, the heart of that T structure is also 1 billion groups. Okay, so the relevant information of the spectral sequence is located on the limit page of the spectral sequence. So I'm going to define that for you. So here's the definition. So some preliminary things. I'm going to write sed er n comma s for the kernel of the differential on that page. And then I'm going to write down a big diagram. So I have the kernels on the Arth page. And of course, since, well, part of the data of a spectral sequence is having like, you know, the R plus first page is the homology of the differentials on the Arth page. I have a surjection down here to the R plus first page. And then I have the kernels here again. Surjection like this, plus 1, plus 2, and so on and so forth. So I have this infinite, take the sag diagram. You can take the limit of that diagram. So that's a sort of iterated pullback construction. And then I take that will itself form a diagram over, well, indexed by the pages, indexed by R. So I take the co-limit that diagram. So this is the limit page, the spectral sequence. And a priori, these are abelian groups, right? And here I'm just taking this limit and this co-limit in just the category of abelian groups. Now, if I wanted to, I could instead consider this as a diagram secretly lying in the infinity, like the derived infinity category of abelian groups, and take like the limit and the co-limit there. So like the limit and the co-limit in a homotopical sense. And then I'll get something that I'll call the derived limit page. So the derived limit page R E and minus. And note here that I'm saying limit here because these are all abelian groups and it doesn't actually matter because what I take the co-limit in, because the co-limit is a sequential co-limits, those are already exact. So I don't really need to care about whether this is derived or not, but I do care whether this is derived or not. And in fact, well, you can sort of rewrite this diagram a little bit, and then you'll see that you can rewrite this limit as a sequential limit. And in fact, a sequential limit only has one derived functor, right? So whatever object you get from taking the homotopy limit here is only going to have, well, homology or homotopy groups in degrees -1 and 0, right? So it's actually not so much bigger. So remark, so it's actually R here. And we only have IE two interesting homology groups of this. If I take this homology group, I just recover this thing, the ordinary limit page, non-derived one. And here I should also mention that we use this notation slightly differently from how it's used in the literature. So typically in the literature, you'll see the limit page as being like an abelian group. Here, in what I'm saying, I'm viewing it as a derived object. And the way that you recover like what is usually referred as R E infinity in the literature, you just take the homology group -1.
Can I ask a quick question about,
Yes.
so this definition makes sense without any sort of convergence hypothesis.
Yes, yes. So convergence has not entered the picture yet, yeah. This is all defined in terms of the data of spectral thickness. In literature. I'll put a little warning here that the notation is not quite consistent. The literature. Right. So okay. I'll just have to do this from memory then. So right. So where does convergence come in, right? So so convergence is really, roughly about the question like, are we like, is the spectral sequence computing what we want it to compute? So, right. So we have this object over here. This is the E infinity page, which, as I just mentioned, is recovered just straight from the data of the spectral sequence. And convergence is somehow about relating this. So this is convergence. Is about relating this infinity page to some extra filtration on the thing we want to compute. Okay, so what is usually the thing that we want to compute, right? So usually, if I think of the spectral sequence as being obtained from a filtration of spectra, then the thing that we want to compute is like the homotopy groups of the underlying object of this filtration, right? So this is typically the so, and sometimes I make this point, I don't know how much I want to emphasize this point in this talk, but really this means that convergence of the spectral sequence, we do typically speak of it as being a property of the spectral sequence. We typically people will ask, is the spectral sequence convergent or not? We speak of it as convergence is some sort of property of the spectral sequence, but it's really not. It's extra data on the spectral sequence, namely this data of like the filtration on the thing that we want to compute and this relationship in between them. If I just give you a spectral sequence, just the data of the spectral sequence, you have no idea how that spectral sequence arose. Like the question of like whether that spectral sequence converges or not doesn't even make sense. Like every spectral sequence will compute something. It's gonna be like some degenerate thing, and that's not the thing that you want to compute, but it will compute something. But it's typically not the thing that you want to compute, right? Typically you have some sort of filtration in mind and you have some object. Okay, so let me write down now what convergence is, because this will give some sort of motivation for this sort of infinite décalage construction. Do we have any questions while I erase?
What is this H-1 term, like, maybe historically, what this R infinity pH, what is it used for?
So it's used for, I mean, I will maybe if you just wait for 5-10 minutes, we'll have the answer. Yeah, but it's some sort of like obstruction to, if you have conditional convergence, it's some sort of obstruction group to having like strong convergence of your spectral fields. That's the short answer. Right. So let's do a little reminder of what convergence is. So I'm going to give you infinity category, some object in C, then the category of filtrations on X is simply going to be the functor category from set up to objects in C over X. So this is filtrations on X. So I think of this, right, as a diagram that looks like this, just S, X. My convention is like they're descending. The interesting object, the underlying object of my filtration is, well, X, which is what I want to, recover in the co-limit. So all of these they map to X. So I have a diagram like this. This is not maybe quite what you want if you talk about filtrations of the thing that we want to compute. Typically, this thing that we want to compute is a abelian group, and then you want not just like a general diagram like this, but you want to make sure that these maps are injections, right? So I'm going to call that a strict filtration. D is an abelian category, then a strict filtration is such that all of these maps are monomorphisms. Yes? Yes.
You want X to be the co-limit of the filtration, or does that come in later on?
That comes in now. So, yeah, but I mean, of course, I want that to be the case, and this is when you call a filtration exhaustive. Yes. So a filtration is called exhaustive. I mean, I have a canonical map from the co-limit of my filtration. It was object X, and if this is an, it's called if it's an equivalence, and it's called complete if, well, I can also look at the limit here. If this limit vanishes. And this may be also a little bit warning. This is also like slightly different from how complete filtrations is used in the context of filtrations of abelian groups. In the literature, typically in such a situation, you have this notion of a filtration being complete and Hausdorff, and now I can't remember which one. I mean, this is a sequential limit, right? So I have like one strict limit and then I have one derived functor. and I can ask that both of these vanish, and the vanishing of one of them is called Hausdorff and the vanishing of the other one is called complete. I don't remember which one it is, but of course completeness in this sense, here I'm thinking of like taking a homotopy limit, and the vanishing of this will mean complete and Hausdorff in the classical sense. But just a little warning. Okay, so now I can trace what convergence is. So weak convergence of a spectral sequence consists of the following data. So I have a graded abelian group. So I'll call A star. This is a called abutment of the spectral sequence. This is the thing that we want to compute. And then I have a filtration on this thing. So, and I specifically have an exhaustive strict filtration. One AN for each N. And then I have the data that connects the filtration with the limit page. So I have explicit isomorphisms. Between, so if I take, and now I should have used AN. So I want to have explicit isomorphisms between the limit page and the quotient of this filtration. Right. And I should also mention, maybe I should have mentioned this in the start. I mean, there's different types of grading conventions of spectral sequences. I think here I'm using like homological Adams grading or something like that. Wanted to know. And maybe I can write this on the same board, but strong convergence which is what you essentially want, is this entire thing with the extra assumption that not only is this filtration exhaustive, but it's also complete. Is weak convergence plus completeness. These filtration for all N. Okay, so this is the thing that we want. This is like,
Can I ask?
yes,
So when you say complete that sequence of abelian groups, do you mean complete in AB or complete in DZ?
no, complete in DC, so complete in difference, yeah. If it's about in AB, then I would have to like complete in Hausdorff.
So even if it's strict, you still need to require that it's inside these and
Yes.
So, I mean, you said before that just convergence doesn't really mean anything. It should be convergence too, right?
Yes.
I'm trying to remember if convergence ever meant anything. So, like, if like 5 or 6 years ago, I don't know, I opened up an old book on spectral sequences. Is there some extra conditions in there which are now superfluous because we have nicer ways of expressing things? Or
No, I mean, this is like the same definition that is in one of these books, right? This is nothing new. I think, so what I wanted to do is just like emphasize that, I mean, the data of this like graded abelian group and these strict filtrations, they don't come to you naturally. Like if I just give you the data of a spectral sequence, meaning like if I give you like the page differentials and then like the isomorphisms between the homology of one page with the next one, like like, where's this coming from? This is not coming from anywhere, right?
yeah.
This is some extra thing.
Yeah.
But from like if your spectral sequence is coming from a filtration, then there is like a there's a natural choice of this. And then you can ask whether the spectral sequence is that you build, the limit page is sort of like compatible with that thing in this sense. And that's sort of what, yeah, if that answered.
Yeah, that answers the
Yeah,
question.
okay. Any other questions? Very good. Okay, so strong convergence of a spectral sequence is like what you actually need in terms of like computations. Like if you don't have, so it means strong convergence essentially means that this thing that you want to compute is abutment is you can actually like build that from the limit page using these isomorphisms in the best possible sense. Well, the problem is, of course, that not all spectral sequences are convergent, strongly convergent in this sense. What should I remove from this? So for this, Boardman has this very useful notion of conditional convergence. So we write this thing down again. Our filtration. In fact, this squiggly arrow, this way of producing a spectral sequence from a filtration is actually functorial. I could actually write down an actual functor from the category of filtrations on spectra to spectral sequences if I wanted to, but maybe not so important right now. So Boardman has this notion of conditional convergence. And yeah. So he says that if this filtration over here is complete, so this is a filtration of spectra, it's complete in the sense of this, then he says that, well, then you say that the associated spectral sequence converges conditionally. So if I think this was maybe like a bit of the starting point of this project, because I think like we all felt like structurally this is not a very nice definition of what conditional convergence is, right? Because in this sense, like convergence is not actually something that's internal to spectral sequences. It's something that kind of like depends on where the spectral sequence kind of arose from. So part of our project is essentially to give a definition of like, what is conditional convergence actually internally to spectral sequence? Like, is there something that we can say, like, is there a definition that we can make that uses only spectral sequences that would be like a reasonable definition for conditional convergence, so that like this is somehow true? I don't want to sort of go there today. I do want to say some few words about conditional convergence. So conditional convergence by itself does not really guarantee any sort of convergence, like not even like weak convergence to, but what it does give you is it does gives you like once you have conditional convergence, there are conditions which is internal to the spectral sequence, which would guarantee strong convergence of your spectral sequence to the thing that you want to compute. So let me write that down. So allows you to deduce strong convergence and here I mean strong convergence with what? With what convergence data? Well, to the graded group being the homotopy groups of X via the image filtration. This means that this thing is these groups. This is typically what you mean when you ask spectral sequence conversions. We do use this sort of data.
Can I ask, is complete also required to be exhaustive?
Sorry?
When you say that this needs to be complete, you don't need it to be exhaustive?
Like in this definition or
The
like?
definition of conditional convergence, you don't require exhaustive.
Yeah, I should, yeah. And exhaustive. I didn't.
When you define exhaustive, I think you required X to be in an abelian category, but that you can make this definition.
No, I mean, you can make this definition, like, this still makes sense, you just take the homotopical limit, like, it's still a sequential diagram, right? That you can take the co-limit, like, even if it's a
Sorry.
diagram of spectra, right?
Yeah,
yeah.
I agree.
Strong and I was remove this. So conditional convergence allows you to deduce strong convergence from conditions that are entirely internal to the spectral sequence in question. I.e. they only depend on this and not on the filtration. Okay, so you can actually write down a little diagram and I'm gonna do that. Write down what these sufficient conditions is. So let me write that here, sufficient. Right here, yeah. For convergence in this sense.
Sorry.
Yes.
So before you said convergence is a datum, it's not just a property. So if you say I deduce strong convergence, do you mean I also canonically deduce the datum?
No, I mean strong convergence using this specific convergence data. That is in the parentheses here.
This specific.
So convergence 2 is a property.
Yes, yeah. So not quite convergence too, because it's not just convergence to the abutment. It also depends on the strict filtration, but yeah. I guess you can think of convergence too as being it. Division criteria for strong convergence, assuming conditional convergence. The little diagram that I'm going to write here. So it depends on what type of spectral sequence you have. And here's the conditions. So if you have a spectral sequence with exiting differentials, meaning it looks something like this, maybe it doesn't necessarily need to look like this, but let's say the spectral sequence is here and then it's 0 all here, so that the differentials are sort of like at some point they're leaving, then there's no conditions whatsoever. This is just automatic. If you have entering differentials, I guess that's the opposite thing. So meaning I have maybe the spectral sequence is not 0 here, and it's 0 here, so that differentials are sort of coming in. Then the only thing that you need to check is that this derived limit page is actually non-derived. So if and maybe this answers your question, Morgan, from before, this is some sort of obstruction once you have conditional convergence to having strong convergence. You can also have a whole plane spectral sequence. I think most of us don't like to work with whole plane spectral sequences because in that case, there's also an extra. So I still need this to vanish, but then there's this extra group that needs to vanish. This is the so-called Boardman's obstruction group. And here I'm lying a little bit because I said that, well, you know, this conditional convergence you should be able to deduce strong convergence from conditions that are entirely internal to the spectral sequence. Of course, we saw before that this data, this derived infinity page, is entirely internal to the spectral sequence. That's fine. We can define it simply in terms of the page of the spectral sequence. Boardman's obstruction group is not quite of that form. It's not actually internal to the spectral sequence, but then there's like extra things that would guarantee, that are internal to the spectral sequence, that would guarantee the vanishing of Boardman's obstruction group. So if you have like no infinite families of crossing differentials, which is a condition that is internal to the spectral sequence, then you can deduce the vanishing of this. Yeah. Okay. So, yes.
When you're saying exiting and entering differentials, can you replace this with like every phase in the page only supports finitely many or receives finitely many?
Yeah, exactly. Yeah.
Point-wise.
Yeah, I think that's what I would mean when I say exiting differentials
okay.
and entering differential. You could have like different, it doesn't need to be like uniformly bounded. The only thing, like, you know, it's a condition like on a specific by degree, which is, I guess, what you mean.
Yeah, okay.
Yeah, I think that's completely fine. Yeah. Right. So I haven't told you what this infinite décalage construction is, right? So far this is like kind of classical stuff. So the infinite décalage construction is something that we introduce in our paper. So I want to say, so I want to say, first of all, that the infinite décalage construction, let me say it this way. So I'm sure that some of you have seen, for example, the décalage construction before. So the décalage construction is one way of, I mean, there's many ways of constructing a spectral sequence from a filtration. You can use like exact couples, you can use like Cartan-Eilenberg systems. The décalage construction is another way of doing this. So the décalage construction was something that was originally introduced by Deligne in his work on Hodge theory, essentially. And it's a way of constructing. So he did this like very hands-on. He was working with like filtrations of chain complexes. And for him, it was a way of like constructing from a filtered chain complex another filtered chain complex so that the spectral sequence that he got from the décalage of the filtered chain complex was like the same spectral sequence, but like shifted forward one page, right? So he did this very hands-on in terms of like, you know, he didn't use any derived methods, you know. What you can do nowadays is you can actually define décalage for filtrations in stable infinity categories in general using something, well, using a certain T structure on on filtration is called a Balin structure. This is what one does nowadays. But in general, the way that I view the décalage construction is that the décalage construction, in some sense, is a homotopy theoretical incarnation of the different pages of the spectral sequence. So you can think of like, you know, the filtration is like page one, and then you take décalage of that once, and you get second page, and then you one more time, and you get the third page, and so on and so forth. So the infinite décalage construction is a way of getting at the infinity page of the sequence. This is something that you're gonna get the iterated page of the spectral sequence by using the ordinary décalage. I'm gonna give you like the infinite page somehow, and the infinite décalage construction is a way of getting like at the infinity page. So if you want to define this, you have to define this in steps. So I'm gonna write down what I just said. So the infinite construction is a homotopy theoretic construction on filtrations that well, it should give you the infinity page, but it turns out, and maybe this is like some of the magic involved, that it actually contains the information of both this derived infinity page and this Boardman's obstruction group in the same object.
Can I ask a quick question?
Yes.
So you might naively hope that like something like like mapping telescope in an appropriate category of the finite décalage construction would give you the infinite one. Is there like a way to see why this doesn't work, or does it work? I don't know.
I don't think it does work. I mean, if you have like a finite filtration, then you know, then there's a way of kind of like recovering like the infinity page from the iterated décalage stuff. But in general, it doesn't work if you just have any like complete exhaustive filtration. Yeah. Okay. So, like I said, we need to define this in steps. So I'm first going to define it for these locally finite filtrations. So I'm going to say that a filtration is locally finite if for every a less than b, so these are integers, the filtration I'm going to take my filtration and at every stage I'm going to truncate it so that the homotopy only exists within these degrees. So if this filtration is finite for all choices of integers a and b, then we say that this is local. Okay. Obviously, all finite filtrations are locally finite. An example of filtration which is not finite, but which is locally finite would be like something like the Postnikov filtration or Whitehead filtration. That's locally finite filtration. And there's a nice characterization of locally finite filtrations, namely that a filtration is locally finite if and only if is complete, and if you look at the associated spectral sequence, if each column of the spectral sequence in homological Adams grading is bounded both above and below, then it's locally finite. So in particular, this means that the spectral sequence is finite in the sense that at some point, you know, like the ER page for some large R is going to be the infinity page. Or maybe I should say this, like, so for each bi degree, if I want the like E infinity n comma s, then I can just take E R n comma s for some large R. Now this R could be different for different bi degrees, but at least for each fixed bi degree. So meaning that the spectral sequence doesn't collapse at a finite page, but at least like for every bi degree locally it does.
Is there an example of a filtration that comes up frequently that is not locally finite?
I mean, any filtration that gives you like a kind of like whole plane spectral sequence situation would be an example of something like that. So, I mean, for me, I started thinking about this because I thought about the Tate construction. So if you take like the filtration that leads to the Tate spectral sequence, then that would be an example.
Okay.
Yes.
I guess if I take A equals B, I get homotopy group in degree A, right?
Yes.
So how far is this from just requiring sort of stabilized isomorphisms and homotopy groups? Actually? So like not using A and B, but just
How far is it?
this condition. Like, do I really need to look at pairs? Can I sort of just fix one? Yeah, that could be monodromy, right? I guess, but
Right.
not, I don't know. Yeah, okay.
I mean, the fact, I mean, I said that there was this characterization in terms of like, you know, each column of the spectral sequence being bounded both above and below. And I guess that would say that maybe it's not so for, I think like it should be enough to look.
This point of the monodromy is quite good. I think like you sort of throw the monodromy out if you actually have this
Yeah.
boundedness type of condition, right?
I wanted to ask, like, what does it mean for such a filtration to be finite?
Oh,
Does it, like,
okay.
just stabilize at both ends?
Yeah, exactly. So it means that at some point there's going to be some finite stage with 0 here, and at some finite point,
Zero.
it's going to be like equivalences here. Yeah, that's what it means to be finite. That
Yeah,
makes
but
sense.
then
Yeah, but
groups
that
of
should be
pi.
enough, right? Point wise, I guess.
So definition. So we're going to start by making the definition of infinite décalage for these sort of filtrations. So for a locally finite filtration, define the infinite décalage thing, and it's going to be a bigraded thing. It's going to have one input and an S. And what I'm going to do, I'm going to take the fiber, the nth truncation of n. This will map into this thing. Make that into a spectrum and then expand that into the correct degree. So here I'm using the same notation as I'm using here. So maybe this I can also call F. Next. Okay. The same notation that I used there. So this is just straightforward definition. First lemma to check, and I think this is pretty straightforward from the definition. Once you have the definition, one can check that if I take the quotient of this thing in the S direction, I get back the limit page of the spectral sequence. Well, I need to be a little bit careful because this is an abelian group. This is a priori a spectrum, so should make this into a spectrum and bend it into the correct thing. So here, there's really no derived E infinity page because, I mean, the fact that, well, the characterization of like each column of the spectral sequence being bounded both above and above and below means that it has both exiting and entering differential. So it's going to not, well, the derived E infinity page is going to vanish automatically. Like it's not going to be non-derived. Another thing that one can see maybe instantly from the definition, one looks hard enough, is that if S is large enough, then for S large enough, this is going to be 0. I'm taking the fiber. So this is just going to be the n plus first truncation of X. And for S small enough, this entire thing is just going to be 0. So the fiber is just going to be the same thing as the source of that map. So in some sense, this infinite décalage construction is something that sort of like interpolates between this and this using the image filtration, right? So it's some sort of like refinement of the Postnikov filtration using the image filtration. Okay. Okay, so far we only really define this infinite décalage construction for locally finite filtrations. So let me now do it for all filtrations. Fine, so if this is complete, maybe I should say complete plus exhaustive, I'm going to make the following definition. I'm going to say that the infinite décalage construction is what you get if you take, well, so I can sort of like truncate my filtration. So before I finish this definition, let me just tell you what these things are. So this is something that we get if we like truncate the filtration so that it only exists in filtration degrees between B and A. So going to look something like this, FB X FB plus. So I mod out by B plus 1 everywhere. And before that it's just 0. And I do this up to filtration degree A. And after that, it's just equivalences, okay? This is a finite filtration. Of course, finite filtrations are examples of locally finite filtrations. So this definition makes sense. I can just use my definition of the infinite décalage construction that I did here. Of course, if this is complete and exhaustive, then I can recover this filtration from these pieces by taking the co-limit over A and the limit over B in either order. And I'm gonna do that here. And this is the thing that makes things work out. This is not at all trivial, so non-trivial is that the infinite décalage construction is actually compatible with this thing. So even if I did this co-limit limit construction outside in the other order, that would give me the same thing. But this is absolutely non-trivial. Okay. I'm going to finish by just writing down the lemmas that are essentially corresponding to this lemma and that lemma in this situation.
How does this relate to just taking the décalage functor as an endo functor of filtered objects and then like taking the colimit over, like composing it with itself?
But what are you taking the co-limit over? Right? I mean, what's the diagram that you're taking the co-limit over? That's the problem somehow.
If I have an endo functor, can I not compose it transfinitely many times?
There's no adjunction unit.
Yeah.
Or is
Ah.
it-
There's no adjunction. Yeah, exactly. There's no adjunction unit, so you can't really, yeah. That's the problem. You can't really like make this co-limit. Makes sense.
I use more liking the differentials.
Oh, the special sequence.
Yeah. Or what is
It's more like the ordinary décalage construct. There's like this shift going on. Yeah. It would-
If you had a map between the décalage and the thing, you would get like a map on associated gradients. But on associated gradients, it's like a function out of a subgroup. And it's a quotient of a subgroup. It's not a. Yeah.
I think these conversations will have to wait
Yeah, yeah.
after because we need to wrap up.
So let me just write down what the definitions are. One is just like the same thing as here, where you recover this, instead of just the limit page, you recover the R infinity page. So if I take the quotient of this thing in the S direction, then yes, the R infinity page, maybe I'll make that into a spectrum and then I spend that n times. And the other proposition is the following. So this is where the R infinity page shows up. Then I also said that this should recover the Borman's obstruction group somehow. And the Borman obstruction group shows up here. So I have a short exact sequence where I can look at, I think, the co-limit of this deck infinity n plus 1, comma s. I can look at the limit s okay. So first of all, we notice that this lemma tells us that if I look at this map, then whenever this is locally finite, this whole limit and this limit is like the same thing. But in general, if I don't have a locally finite filtration, I just have any complete exhaustive filtration, there is actually a difference between this thing and this thing. And the difference is only the difference in one homotypic group. Yes. And this is Borman's obstruction. And I think this is actually Borman's obstruction group in degree n plus 1. It's a little bit annoying, but you have a short exact sequence like this. So Borman's obstruction group sort of shows up as a sort of obstruction to these two things being the same thing. So it's a sort of like extended completeness condition you can kind of think of. Or by graded filtrations. Okay, let me